Hello and welcome to today's Prism Sound educational webinar. Today we're going to be talking about active loudspeaker system analysis, or powered loudspeakers for those of you who use that terminology. We're talking about loudspeakers that have integrated electronics including amplification, and we're going to be talking about the various different modes of functionality that system may incorporate, and we're going to be looking at some examples of how we can use modern test methodologies to analyze that system and all of its constituent parts. Before I give you an agenda for today's session, what I just want to do is to involve you a little in today's proceedings and ask you for a little bit of interaction. What I'm going to do is switch straight to my test and measurement system, which I will be explaining in more detail a little later on, and I'm going to make a quick frequency response measurement of a loudspeaker that I have in the room here with me today. I will do that now, so I'm going to press the test button here, and you can see on your screens there, if you're familiar with measuring loudspeakers acoustically, then this yellow trace is our frequency response. And this has been derived by taking our green trace that you see on the screen as well and applying this turquoise coloured time domain window, which you can see here. If I drag this window to the left or the right, you can see the impact on the frequency response measurement. More on that later, but what I just want you to do for me for now is to tell me whether or not you are familiar with this type of analysis methodology. So I'm going to post a survey question, which you will see on your screen very shortly, and that survey will just ask you to answer that question for me, to tell me whether you know what this type of analysis methodology is called. There is then a second question just asking a little bit about your background. What is your primary area of interest in terms of the test and measurement topics we will be covering today? There are quite a lot of you on this session, so I'm just going to wait a few more seconds for those of you that want to answer to get a chance to complete that question, or the questionnaire rather. So I'll leave it a few more seconds, 3, 2, 1, and I will now stop the survey, and hopefully you can now see the results. So just around about half of you got a chance to answer the question there. We have 100% success. Excellent, that is a first. All of you were able to successfully identify the fact that the analysis methodology we've just been looking at is known as an impulse response, to which we then applied a time domain window to obtain our frequency response. And it looks like the majority of you have an interest in both electronic and acoustic testing, which is good news because I have prepared some demonstrations for both of those areas of audio functionality. So what I'm going to do now is go back to my slideshow and just give you an overview of what we're going to do in today's session. So as we've already alluded to here, we're going to be talking about the electronic analysis and acoustic analysis that one might want to undertake if you are attempting to quantify a loudspeaker system that might include a degree of other components, including power amplification in the case of a powered loudspeaker, and several other areas that we're going to take a look at as well. It seems that you, as participants, believe that this is important to be able to analyse both electronics and acoustics, and we believe so too. Just to put this into context really, I've just got a slide here showing you some of the very broad and diverse range of loudspeaker products that are on the, in particular in the consumer audio market today. Many of these products traditionally would not have been thought of as an audio product, but they incorporate audio functionality and active loudspeakers in many of these types of devices. So there has been a very large increase in the number of engineers and the number of engineers working on audio design or products with audio components within them. And that has led to an increased demand in audio test systems, but at the same time, the audio test systems that engineers working on these kind of products are using has needed to follow the trend of expanded functionality and increased analysis capabilities. So we're seeing demand from our customers to provide ever-increasing levels of audio test functionality to cover the various different ranges of operation that these products encompass. So hopefully that sets the context for you for today. What I'm going to do is to carry on showing you some slides in my PowerPoint slideshow, but I'm going to intersperse that with some live measurements that I'm going to be making using the Prism Sound D-Scope 3 audio test instrument, which I will introduce you to in a bit more detail shortly. How am I going to do this? Well, I have a pair of powered loudspeakers on my bench in front of me here today, and I have just I've bought a relatively low cost off-the-shelf USB powered loudspeaker for the purpose of illustration. As I say, this is USB powered, so it receives its signal and its power via the universal serial bus, and the acoustic components of the loudspeaker are that it contains a pair of 1-inch full range micro or mini drivers per channel. It's a stereo system, and it's a 1.5 way design in that there is one channel of power amplification and there is a capacitor in parallel with one of the drive units, so that at high frequencies only a single drive unit radiates, and at low frequencies both drive units will be radiating. And it's a sealed enclosure. So that is my demo system for today. That's what I'm going to be using as my equipment for analysis. And in a more general case, an active loudspeaker may include some or all of the following areas of functionality that I'm just about to identify. In some cases, for example headsets and this type of loudspeaker, you may have a USB audio interface where you need to verify that the audio drivers and the audio signal path through the USB is intact and doing what we expect it to do. There is a good chance that at board level, on the printed circuit board, you may have digital audio signals being routed from various integrated circuits from one device to another. And so we're going to take a look in a bit of detail at that. Being an active loudspeaker, there is a very high probability, almost a certainty, that there will be some equalization or filtering applied, either in DSP or potentially in passive or active crossover networks, to distribute the spectral content of the audio signal to the appropriate drive units for the frequency bands that we're interested in reproducing. In a more simple system like the one I'm looking at today, there may well be some EQ in there to prevent the drive units from receiving too much power at low frequencies where they cannot handle the excursion, and likewise to increase the headroom of the amplifiers by limiting the frequency range of signals the amplifiers attempt to reproduce. We may have some dynamic processing on board the system as well. Again, this is potentially to help with protecting the system from overload or unintentional abuse. And by definition, a powered or active loudspeaker will incorporate a power amplifier or power amplifiers, depending on how many drive units and what spectral range of signals those drive units are intended to handle. And of course, we will have some electroacoustic transducers, and in almost all cases we'll have some kind of acoustic enclosure to mount the drive units and to remove the radiation from the rear of the diaphragm. So what kind of tools are you likely to need if you are designing or verifying or manufacturing these kind of products? On the simulation side of things, there are a range of products that you may find useful to assist you in the design process, and these can range from finite element simulation packages for the motor structure and the moving parts, through to simulator packages to help you design and optimize an appropriate enclosure. You may have circuit simulation tools that allow you to design and optimize the amplifiers and the signal processing. And in particular, you may well be used to using some kind of crossover simulation package to emulate the performance of the system with some hypothetical crossover circuitry in the simulation. We're not going to talk about simulation and design in detail today. However, Prism Sound do offer a range of tools to assist with the design and simulation of loudspeakers. From the Danish manufacturer of software and test equipment, Loudsoft. We are a representative for Loudsoft on a global basis, and if you'd like to learn more about these design and analysis tools, we will be running future webinars giving you some further educational information about the Loudsoft product range and how it can help you. Today we're going to be focusing purely on the analysis side of things. So typically on your test bench you may have one or more of the following devices to assist you in designing or testing a loudspeaker system. You might have a dedicated acoustic measurement system. That may well be independent of your electronic test system. It's fairly likely you may have an oscilloscope in your lab or on your bench, and perhaps for dealing with some of the digital audio signals you may be handling, you might have some kind of logic analysis system, and also potentially some USB analysis tools. Now we're going to be looking at the D-Scope Series 3 test solution today, which provides you functionality to address all these different areas of audio functionality that you may need to verify and test as part of your design or testing role. So this is the tester measurement system that I have on my bench, and this is what we will be using when we start making measurements. It centres around this grey instrument here, which is the D-Scope Series 3 audio analyzer that we Prism Sound manufacture and supply. There are a number of peripheral components that you can see in the diagram here, or the photo, including the loudspeakers themselves. I will talk you through the individual test setups in more detail as we get to them. So I'm going to start by looking at the Windows audio device interface, in this case looking at the USB functionality of this loudspeaker. So how am I going to do this? Well, I have my D-Scope Series 3 system on my desk here, as you have just seen, and it comprises a hardware interface for generating analog and or digital audio signals. And that hardware interface, this instrument, connects to my host PC, the laptop that I'm using here today, by USB. And the software allows us to control what signals are generated and how we analyse them, and also displays results on screen, which you will be able to see during this presentation. So I have connected my USB powered loudspeakers to my host PC, and I can use the D-Scope software to generate signals and route them directly through the USB interface to the loudspeaker, which we will see very shortly. For this first test, I have then taken an analog output signal from the device. So I'm actually probing the printed circuit board inside this loudspeaker at the output terminals from the digital to analog converter. That chip also happens to be the USB interface chip, so it's a combined USB and D2A converter chip. One of the really interesting things that we're going to take a look at, and one of the powerful tools that we have inside the D-Scope system, is the ability to look at signals and analysis results over potentially indefinite duration. We have a tool called the Event Manager that allows us to look for intermittent problems. And when we're talking about a USB powered or a system that incorporates USB audio interfaces, we may be interested in looking at its stability over time and whether we're suffering from any packet loss problems or any other associated USB timing and data issues. So in order to do that, I'm going to switch back to my D-Scope Series 3 audio test software, which you now see on your screen. For those of you unfamiliar with the D-Scope operating environment, the idea is that we are providing a universal, flexible and powerful analysis tool that allows you to set up a series or even just a single test to do all of the analysis that you require in a particular mode of functionality. So, for example, I can open up my signal generator, I can open an analysis instrument. These can be positioned and dragged around wherever you want to set them up. I can then save this configuration file, there is an option here, and reload that configuration file at a later date to recall those same test setup parameters that will allow me to make the same measurements in the same conditions. What I have done to make things a little more simple for this application of measuring active loudspeakers is I have previously configured a series of tests that you can see have been positioned on my user bar at the top of the screen here. So the test that I want is actually this one here, USB audio. I could browse to it through the Windows menu structure here, but I just want a quick link here, a quick and convenient button, so I hit this, hit OK, and I'm going to go straight to my test here. One of the things that you see on screen in front of you here is this this yellow post-it note that I have on my screen, and that's just something that I can write in the D-Scope software, and this is giving me a quick notification that if I want to make this next measurement successfully, I will need to reconfigure my hardware connection. So I've just connected a different cable, and I will now just turn that memo off. I'll just hide that. Okay, so what I'm going to do now is I'm going to go to the sound card outputs panel in the Dscope software, and I'm going to look for the output device that I want to route audio to, in this case the loudspeakers that we're going to test. Now this is an additional I/O that we give to you on top of the digital outputs and the analog outputs. Here is the menu up here. So I'm going to look for the loudspeaker that I have connected, which is this one here, and as you can hear in the background, the system has come to life. I'm going to turn the volume down on the loudspeaker just while I'm talking so that this doesn't disturb you. It's worth noting that we're using a telephone here to transmit the audio, so it may not appear as a very low distortion sine wave when you listen to it down the telephone line, but that's how it sounds at my end. It sounds crystal clear. So what am I attempting to do in this measurement setup here? Well, firstly, down at the bottom right hand corner of the screen here, I have our continuous time detector tool open, and this is a real-time analysis instrument. I'm just going to go to the architecture of this instrument so you can see it in a bit more detail. It is a flexible and highly configurable analysis instrument that gives us a number of different filter settings that we can dial in or choose from a preset, followed by an amplitude meter. So this is a filter driven voltmeter that allows us to do things like, well, let's take a look. It allows us to measure parameters such as THD plus noise, intermodulation, distortion, gain, crosstalk, all the kinds of real-time analysis functionality you would expect to see in an audio test instrument. There are a number of other instruments in the Dscope software, and in particular later on we're going to look at the FFT processing tools and see how they can really enhance the power of a test instrument by providing spectral analysis tools. But for now I want to use a continuous time tool because the test method that I'm about to employ requires that we do that. What I want to do is set up a test using our event manager that will allow me to check for dropouts, packet loss in effect, over the USB interface of this loudspeaker that I'm testing. Now in order to do that, I've set up a THD plus noise filter, and I'm going to be analysing the residual output of that filter, so just the noise and distortion. And what we will see is that if there are any even very short duration glitches, we will see a significant change in the peak output of this continuous time detector. So in order to be able to set this measurement up, I need to switch my analysis response to peak to reliably pick up even the shortest duration of glitches or dropouts. So I'm going to turn my level up in just a second. Before I do that, I'm just going to bring a few measurements up on the screen here so that you can see them. And these are monitoring in turn the amplitude, the frequency and the THD plus noise of the output from the D to A converter chip on this loudspeaker. Now I have set up some limits on this. You'll see that the distortion reading is currently breaching the limit because I have turned its level down. When I turn the level up again, you will see that this reading is now within range. I'll turn that down just for a second. So what I want to do is to illustrate to you how you can set up a test and leave it running over potentially indefinite duration. And we can use this event log file to log any deviations from the results that we're expecting to see. And as I explained, this THD plus noise residual measurement, when set up into peak mode, is a great way of analysing whether we are experiencing any glitches or dropouts due to communication issues over the USB interface. So what I'm going to do is turn the volume up, reset the log file, and I'm going to do something fairly crude. I'm just going to turn the level briefly down a long way and then straight back up again, and that will emulate a brief click in the signal path. And I'll turn the generator off now just so we don't all go mad. And what you'll see there is that when we saw these reading limits being breached, the errors were being written into this log file. So complete with a time and date stamp, we see exactly what the error was that has led to this log being created. So this is a great tool to set up and walk away from. You don't have to sit in front of it. You can check for these kinds of intermittent problems, and there are many potential intermittent problems in this type of product. I've just identified one potential issue here and how we'd go about testing it. So I'd like to conclude that measurement there. I'm going to go back to my slideshow here and talk about the next example that I'm going to show you. And I'm going to be looking at board level digital audio interfaces. Now, I have labelled this I2S. That is terminology that if any of you work in digital audio electronics will probably be familiar with. That is a standard digital audio interface, a serial interface that is used at PC board level to transact digital audio data between integrated circuits on your circuit board. Now, we have a solution for analysing those kind of serial digital audio signals, and I'll just show you how we do that. So once again, I have my D-Scope test system set up with the hardware and software running in parallel. I'm now also using one of the peripherals that you saw in the photo earlier, which we call the VSIO adapter. And this allows you to convert D-Scope's native AES EBU digital audio format signals to and from serial digital audio formats such as I2S. And it also gives us I2C control capabilities so that we can actually send control data to the device that we're analysing also. So in this case, I would once again have my audio being routed via USB to the loudspeaker I'm testing, and I can then apply probes to the printed circuit board that allow me to either send digital audio data to the PCB or to analyse what's already being generated on the PCB at serial digital audio level, or potentially both. I can route signals in one or both directions. And I'm going to take you through a very brief tour of this in the D-Scope test system here. I'm just going to again take a shortcut to the new configuration file here. I'm not going to dwell on this in detail because there are very many potential complications that you could encounter depending on the device that you're testing. You need to make sure that you have scrutinized the datasheet for the integrated circuits that you're attempting to analyze so that you can be sure that you have set up the correct clock and data formats for that device. All I'm going to do is route some digital audio into the board and back out again, and in fact I'm just going to do a loop through measurement, so I'm not going to do anything too sophisticated here, but I'm going to emulate one of the valid tests that you might want to undertake, and that is to verify that the digital audio data that I am sending into the board comes out at the other end with exactly the same data. In other words, it's a digitally bit transparent path, which is one of the tests you might want to undertake in certain situations. So there are a great number of parameters that we can set up in the VSIO adapter control here. Just turn that down a second. And you can set up the generator and or the analyzer depending on which direction you are wanting to send or receive data. And here we have parameters that allow us to, for example, determine whether the device that we're testing is the clock master or whether our test system, the VSIO adapter interface, is acting as the clock master. We can, for example, invert the polarity of our serial clocks or our word clocks, and we can change the format of them. This is really just designed to allow you to set your clock and data formats up to match exactly the device that you're testing so that you can transact your digital audio data successfully. I have set my system up at the moment where I'm just routing digital audio into and back out of the system, and at the moment I believe I have the generator open here. I'm just generating a sinusoidal signal at an amplitude of 0 dBFS and a frequency of 1 kHz. So if I take a look at the trace window that we provide in D-Scope, I can now see that there is my sinusoidal waveform in green and there is my FFT data shown in red. Now what I'm looking at here is what ought to be a digitally transparent 16-bit audio signal path. And so here where we measure THD plus noise, we see that we've actually got about minus 94 dB, which is the theoretical limit for that particular channel. And I've got a couple of readings tracking the amplitude and frequency. Now that helps us to set the system up, but what we really want to do is to check whether the system is behaving as we would expect, i.e. it is digitally transparent. So what I can do is select a stimulus here called the channel check sequence, and this allows me to automatically check every single data bit that's being received at the input to the test instrument and verify that it is truly bit transparent. you will see that these lights have turned green at the bottom of the page here, and that is a verification of the fact that this system is behaving bit transparently as we would expect. If I just switch between the channel check sequence and the generator stimulus, the sine wave we saw, these lights have now gone red and back to green again, indicating that a second or two ago we had a failure in the bit transparency because this test sequence was not reaching the end of the signal path. This test sequence is just a pseudo-random bit sequence that's known by both the generator and the analyzer, and therefore we can numerically determine whether each bit is correct as it arrives. Now, what you don't really want to do is to sit here in front of the test system looking at this green light for hours on end. You want to ideally set this up and walk away and come back later. And once again, we can use our event manager in order to be able to do that. So if I just reset this log file here, now got no data in the log file, I'll do exactly the same as I did a second ago. I'm going to switch to generator as my stimulus here, and you'll see that the red lights have come on telling us that we've got an error in the data sequence here, which has now been reset, and you can see that once again this information is being written into the log file. I'm going to leave that there for now. Digital audio is a whole other topic in its own right, and as with most of the things that we're going to talk about today, we could talk at great length about any of them, but I want to move on to the next topic here. And we're going to look at the equalization and or crossover circuit that may be a part of the loudspeaker system that we're analysing. Now, I just want to ask you another question before I go on with this here. What I'm going to be looking at, because we're talking about EQ and crossovers, I'm going to be making some frequency response measurements. And that may well be something that you have experience of doing yourselves. I would suspect that is almost certainly the case. I'm going to ask you just a very quick question about how you, in your experience, have made frequency response measurements, or if you've never made them yourself, the kind of measurements that you're aware of. So let me just start this survey. Again, there are quite a number of you on this conference, so I'm just going to give you all a reasonable amount of time to respond to that survey if you wish to. And I'll probably give it another 4 or 5 seconds, so 3, 2, 1. Apologies if you didn't get a chance, but I'm now going to stop the survey and let's take a look at the results. So, the majority of you that have responded have used pink or white noise stimuli as a method for giving you the capability to analyse frequency response. Some of you, I suspect possibly the electronics engineers amongst you, have used sinusoidal sweeps in the past. The majority of the respondees have also used impulse response based techniques, which we saw a bit earlier and we'll return to later on. And a good number of you actually have used multitone techniques. Now, multitone is actually one of the things that I wanted to focus on here, and we're going to look at a particularly powerful form of a multitone stimulus that's useful for measuring frequency responses. So let's just take a look at how we're going to do that. Well, once again, my test setup hasn't changed vastly from the original setup, but what I'm doing this time is I'm going to look at the analog output either at line level or speaker level after any EQ processes that are happening in my loudspeaker system. So, moving back to my D-scope system again, let's load my new configuration file, and I'm going to talk you through the theory and practice of implementing a very fast frequency response using a method that we call the bin centers stimulus method. So I'm going to go onto my page 1 tab here just for a second and show you that I have selected this bin centers stimulus as my signal generator function. What is that? Well, it's a very densely packed multitone that has, in this case, because of the selection that I've made here, it has 8,000 tone components within it. Actually, technically, there are just over 4,000 tone components in the real frequency axis between DC and the Nyquist limit, or whatever frequency range we specify. The point is that if I choose an FFT size that equals the size of the generator function, in this case, again, 8,000 points, and use a rectangular window function, what we find is that because we have specifically engineered this bin center's signal here such that the individual tones align exactly with the center of each bin in an equivalent sized FFT, when we join up those dots, join up those data points by plotting an FFT, we actually see we get a frequency response. Before we do that, I'm just going to show you what this bin center stimulus looks like if we use a very large FFT size. So in this case I used a 64K FFT, and you can see that there are a series of discrete sinusoidal components at all of these individual tone frequencies. On my logarithmic x-axis scale, these become apparently more densely packed together as we go up in frequency. That is just simply because these tone components have an equal spacing on a linear scale. So on my log scale, which we as audio engineers quite often use, these appear to become more compressed, or closer together I should say, to avoid any audio terminology ambiguity there. So that is what the bin center stimulus looks like if I analyse the FFT with high resolution, and this is what it sounds like. So hopefully you could hear that there. That is a wideband stimulus. It's rather noise-like in its character. What I'm going to do now is turn on my live FFT trace, and this FFT measurement is actually plotted with exactly the same number of data points as the stimulus, so in this case 8,000 points. That gives me 4,000 points of data in this frequency response measurement, and although you can't really see it terribly clearly, it's updating at a very fast rate. This red bar at the bottom here shows you the progress rate, and we're getting several, 3 or 4 frequency response measurements every second. Now what I'm going to do is cheat a little here. I have an outboard effects processor that I'm going to use to make some dynamic changes to my frequency response, so we can see this updating in real time. Let me just bypass that device, as it were, and what I'm doing here is I'm implementing a high pass and a low pass filter initially, and you would have seen that result updated very quickly, but to give you an idea of just how quick that was, what I'm going to do now is manually adjust the frequency of my low pass filter, which is currently set to approximately 3 kHz. So I'm making some adjustments here, and hopefully you're seeing quite clearly just how quickly those individual frequency responses are updating. So this is a really, really powerful tool if you need to do a large amount of analysis on a system that perhaps has some variable EQ, whether it's bass management or adjustable crossover slopes or anything that needs a large number of frequency response curves to be verified as part of the analysis process. So I'm just playing with the low pass filter now. What I might also do as a potential loudspeaker designer is to dial in a notch filter to deal with a cone resonance issue around about 4 kHz. So there you can see I'm just dialing in a slightly different flavour of EQ as well. So this is a great way of making frequency response measurements, particularly electrically. This is an electrical measurement I should have added at the start there. And it gives us a really powerful and flexible way of measuring many different curves in a very short space of time. Once again, I want to move on to the next subject and not dwell too much on that for now. So I'm going to talk a little bit about dynamics processing, and potentially we're talking about either compression or limiting here to either adjust the dynamics of the signal because that's the way we like the sound, or particularly in the case of loudspeakers, to prevent the system from becoming damaged if we have a signal that is too high in level at the input. It's a very similar setup to last time. In fact, it's almost identical. I'm taking an analog output signal from the system, and that's what I'm going to be analysing at the D-Scope Series 3 analog inputs. Oop, just come out of my slideshow there. So let's go back to my test system. I'm going to bypass the EQ just so that doesn't mess up my subsequent measurements. Let's just return that to where we had it. And now I'm going to switch to my dynamics processing setup here. I've got two test setups that I'm going to talk you through. One of them deals with the steady state response of my dynamic processing circuitry, and the other deals with the transient response. Now what I'm going to do in this first test is do a very straightforward transfer function analysis. So I'm going to set up a sweep, which by the sounds of things many of you have already had experience in dealing with. But just to explain, what I'm going to be doing is measuring amplitude, so the output amplitude of the compressor circuit, and I'm going to be varying the input amplitude. So in effect what we're going to see on this graph here is on the x-axis this is the input amplitude to the device we're testing, on the y-axis this is the output amplitude, so we'll see a transfer function. And in the first instance, the first test that I'm going to run, I have the compressor bypassed. Once again, just to confirm here, I've got an outboard compressor that I've looped into the signal path just to allow us to make some quick changes. So with the compressor bypassed, what I would expect to see would be a straight line with a gradient or a slope equal to 1. In other words, our input and output amplitudes will equal one another at each sweep step. So I can run this sweep now, and you can see the amplitude increasing on my time domain trace at the same time as our sweep result updating on the trace window here. And as we can see, we've got a straight line with the gradient of 1 that we were expecting to see. Now if I engage my compressor, which I have just now done, I can rerun this test, and in this particular test I've got a compressor with a threshold of about minus 10 dB relative to full scale. So in other words, at 10 dB below maximum output, the compressor will start to engage and limit the output level. So run the test again. And actually that looks like I've changed the compressor settings, but you get the idea there that at the upper end of the amplitude range here we start to see the compressor activating. Let me just see if I can adjust this. Let me just run that test again. And there we have it. That's the knee at 10 dB below full scale that I was expecting to see. So this gives you an idea of the steady state behaviour of the compressor that we're testing here. And of course I've had to be a little bit careful because this will take a certain amount of time. One of the parameters on the compressor is the attack time, and I've had to ensure that I've built enough settling time into the analysis routine here to ensure that the compressor has settled to its steady state amplitude before I ask Dscope to make a measurement. So I have assigned a settling time of 50 milliseconds here, knowing that my compressor settling time is about 20 milliseconds. So that deals with the steady state response, and what I want to do now quickly is just show you how we can begin to analyse the transient response, the time domain behaviour of this compressor. And what we can see here, and what you could have heard in the background, and I'll turn it up in a minute, is a time domain signal. So we're actually looking at a time domain waveform. The units on the time base here are, this is 680 milliseconds, so this is just over half a second of data. Hence it looks like a solid block. If I just zoom in here, we can see that this is indeed a sinusoidal signal. We call it a burst stimulus here, and this burst stimulus allows us to vary the amplitude of this signal. So I'm starting with a low amplitude of minus 40 dB relative to full scale, which is this region here, and I'm then switching to a signal that has the same frequency but with an increased amplitude of 0 dB relative to full scale, which is this portion of the signal here. So when I zoom right out, you can see that this looks like a solid block of colour now because of the amount of data in there. I'm just going to turn the stimulus up, so hopefully you can hear that. The pulsing in the background corresponds to this stimulus that I've set up here, where we are varying the amplitude with respect to time. Now if I turn on my live time domain trace, you can see that this green measurement now is showing us the time domain response of this compressor once the compressor has been engaged in circuit. And I can now do things like adjust the attack time. So I'm just going to turn a knob on this compressor here. I'll just do that now. So I've just ramped up the attack time to 200 milliseconds, and you'll see that we've now got a very different result. Just to zoom out there, so you can see that this is actually behaving symmetrically, which is what we would expect to see. So we can now start to get a feeling for whether this compressor is doing what we expect it to do, verifying whether its performance mirrors what we would expect to see. I'm going to leave dynamics processing there and again move on to the next topic, and we're going to talk about power amplifiers. Now, as I said earlier, each of these topics that we're discussing here, all these various areas of functionality, are topics that really we could talk about at great length all on their own. And in fact, we have already run a webinar dealing specifically with power amplifier measurements, and these various areas of functionality we'll be covering in more detail in future webinars as well. So I'm going to take you through just a very quick couple of demonstrations of what you might want to measure from your power amplifier, but bear in mind that there is obviously a lot more that you may need to know on any of these subjects we're talking about. So once again, I have my D-scope test system, I have my active loudspeaker connected. This time I have introduced another component in the signal path, or another part of the audio test system, and this is a passive low-pass filter. The reason for using this low-pass filter is that this particular device, I happen to know, has a Class D power amplifier built into it. And Class D amplifiers have a relatively large amount of out-of-band noise as a consequence of the switching frequency, or the internal switching architecture. And you see residual components from that switching content appear out of band. Now, this audio test system is designed to measure signals up to about 100 kilohertz, and that out-of-band switching noise is not something that we actually want to enter the test system. It can potentially cause issues with the amplitude ranging circuit at the front end of any audio test instruments. So it's standard protocol to offer a passive low-pass filter solution, a calibrated low-pass filter that allows us to remove the high-frequency switching transients that may give us difficulties with our measurements otherwise. So I've connected the low-pass filter in series with the output from the terminals of the power amplifier. So once again, I have probed internally inside this loudspeaker here. One of the things that we're going to look at, we're going to have a look at a couple of different test setups here. Initially, we're going to look at quantifying the output power from the amplifiers, which is one of the first things you're likely to want to do, having designed, built, or attempted to verify the performance of a power amplifier. We're then going to move on to some very interesting spectral analysis tools, some really unique and powerful tools that we have in the D-scope system in particular, that exploit the power of the host PC to do a lot of numerical calculations and post-processing on FFT data, so spectral processing. And we have a series of instruments called our smart FFTs, or FFT detectors, that we're going to look at in more detail and see how they can really help us to understand how our device under test, whether it's a power amplifier or any other kind of audio device, how it is really truly performing. So I'm going to load my first configuration file that relates to the power amplifier testing, and as I said, this first test is going to be related to analysing the maximum output power of my amplifiers. Again, I've just written a little note to myself in my configuration file here to connect my low pass filter, which I have duly done, and I can then minimise that memo. So I've got a test set up here that allows me to analyse the total harmonic distortion plus noise and power output of my amplifier all at the same time. Now, in order to measure in units of power, what I need to make sure that I've done is told the test system something about the load impedance that my power amplifier is delivering current into. In this case, I've measured the impedance of the drive units, and the nominal impedance is in the region of 10 ohms. So I've dialed 10 in here as my impedance reference, and that allows me to select units of watts in my signal analyzer here for the purpose of my power measurement. Now, what I could do here is turn on my signal generator, starting with a relatively low amplitude to begin with, and I could try dialing in different amplitudes here attempting to find the point where my THD plus noise reaches a predefined level. Now, for the purpose of most engineers, we would talk about either a 1% or a 10% THD plus noise limit, that being the limit where we say that we are going to obtain no more useful output power from our amplifier. We have reached the onset of clipping, and therefore that is how we quantify our maximum output power. Now, different groups of engineers use different standards. For the sake of my demonstration, I'm going to be looking for the point where my THD plus noise reaches 1%, and I'm going to define that as my onset of clipping. You could choose whatever threshold you wanted here. Now, as I was saying, you could simply manually adjust the signal generator amplitude. You could even use a slider here to help you. But that would be a relatively slow process. It's an iterative one that requires a fair amount of manual input to keep an eye on the distortion measurement here and to determine exactly when you've reached the onset of clipping. A more powerful way and a more clever way of doing this is to use what we call a regulation routine. So here I have stipulated that I want my continuous time detector measurement of THD plus noise to be the measurement that I'm attempting to regulate. And I'm attempting to regulate it to a value of 1%. As we've just discussed, that is, for the sake of my argument, the onset of clipping that I have defined. And my source here is that I'm going to vary the signal generator amplitude in order to seek out this value of 1% THD plus noise. Now, this is about to get a little noisy from my point of view, so I won't attempt to talk over it, but I'm going to hit this regulate button and keep an eye on the THD plus noise reading here, the output power reading here, and in the trace window here we will see two traces. The green one will be the time domain waveform, our sinusoidal signal, which will at some point start to clip, and we will also see the residual output. The residual output being the output from this filter here. So we're applying a 1 kHz notch filter in order to measure THD plus noise, and we can actually look at the time domain output from that filter in this light blue trace, and you will see when we start to reach the point of clipping, we will see harmonic distortion products appear in that residual waveform. So onwards, let's regulate. And I've just realised that I've started a very low amplitude there, which is not what I wanted. So you'll see there we've got a notification telling us that the regulation has been successful. We have reached our target value of 1% THD plus noise, and if we take a look at the time domain data in slightly more it's in a slightly closer up view, we can see that we have indeed reached the point here where we're starting to see clipping in the time domain waveform. And of course the residual waveform too is also showing signs here of the harmonic distortion products that we expect to see when we run into clipping. And that has occurred at an amplitude of 864 milliwatts. In other words, we've got just under 1 watt of electrical output power from this USB powered amplifier, which is broadly typical of the kind of output power you could expect from a USB powered device. So the second test that I want to perform on my power amplifier here is, as I alluded to earlier, a spectral analysis. I'll just turn my signal down a little. What you can see on my trace window here is the FFT spectrum of the output of my power amplifier, driving current into my loudspeaker load. Now, my stimulus in this case is quite simply a sinusoidal waveform, and what we should expect to see in an ideal world is a nice clean peak of energy at 1 kHz and very little else anywhere else. Now, of course, that's not going to be the case. We expect to see some harmonic distortion products. There may be other noise and distortion products in the FFT that we're interested in analysing too. What I'm going to do is, rather than having all these numbers updating and me having to talk over the stimulus, I'm just going to capture a measurement there and turn the level back down again. So you would have seen that these numbers were all continually updating and giving us close to real-time feedback in terms of what our circuit was doing, and we could be refining our circuit as we're making all these measurements and tracking the trade-offs between them. So what are these? Well, I'm sure many of you will be familiar with the idea of using an FFT to analyse distortion and noise products, but it only goes so far. And what the smart FFT instruments on this side of the screen allow us to do is to put numbers on some of the information that we see in the FFT spectrum here. We can see approximately the relative levels of these distortion products, but it's very hard to actually put a number on them just from simply FFT data alone, because we need to be able to account for the time domain window function that we've applied prior to the FFT process. And for example, when we want to analyse noise, we can't simply read off the point at which this noise floor here intersects the y-axis, because that is not the noise floor of the system that we're measuring. Each of these data points represents a noise energy at a particular range of frequencies, and we need to integrate all of them if we want to analyse noise. So whilst this is useful information in the FFT, it doesn't give us precise numerical data, and that's the kind of thing that we're looking for when we're analysing closely the performance of something like a power amplifier. So let's start up here. One of the measurements that I'm measuring here, and was measuring live before I captured this result here, is THD plus noise. I'm just going to turn on a previously measured result where I've actually done a bit of averaging here to clean up this trace a bit. You can see that THD plus N is reading minus 50, nearly minus 51 dB. How is that being measured? Well, we're implementing this light blue, this turquoise notch filter here, removing the 1K component prior to integration of the remainder of the signal. And you can see that this is an ideal, it's a perfect brick wall notch filter, which is something that you can't do with the kind of real-time analysis instruments that we saw earlier and perhaps you may be familiar with. But this is a really powerful way of just removing or just including very narrow band spectral components within our audio analysis. Now we know that THD plus noise is useful from the point of view that it gives us a standard measurement against which we can compare a number of devices, and many manufacturers will quote THD plus noise figures, but it's not terribly useful as an engineer in terms of what it does or doesn't tell you about the performance of the product. For example, is our THD plus noise figure dominated by noise or is it dominated by distortion? Well, the FFT data can tell us that, provided we can get numerical data out of this FFT spectrum. And that's exactly what these smart FFTs can do, or one of the things they can do for you. So you can see here I have a noise measurement added to my configuration file here as well, and just to show you how that's being derived, I will turn on this trace here and you'll see that we now have a bank of 20 ideal brick wall notch filters removing all of the harmonic products and the fundamental. So this is just allowing us to see the remainder, the residual, after we've removed the noise and distortion. After we've removed the fundamental and distortion, i.e. we're just left with the noise. And likewise here I have a measurement where we're looking at the THD only, so that's just the total harmonic distortion, and for the sake of limiting this to a 20 kHz bandwidth, I'm looking at the 2nd to the 20th harmonic of the fundamental 1 kHz tone. So already we can now see that in this particular device, in this power amplifier, our THD plus noise measurement is dominated by harmonic distortion. The noise is some 10 dB lower than the distortion measurement. So having established that, well, we might want to know a little more about the harmonic distortion products, and again we can use the FFT trace as a quick visual guide as to the relative amplitudes of our harmonic distortion products, but we might want to put numbers on them, and that's what I've done here. So I've got a measurement of the 2nd harmonic distortion energy, the 3rd, the 4th, the 5th, the 6th, you could go on. I'm also measuring crosstalk here. You can see that there is a component at 700 Hz, which is coming from the generator on the opposite channel. I've used a generator stimulus with a 700 Hz tone on one channel and 1 kHz tone on the other. So here we can measure crosstalk at the same time as making all these other measurements. I've got a analysis filter here configured to show me the mains hum. I've just lost my FFT, there we go. And this is, in this case, the mains filter is integrating the energy in the first 5 harmonics of the mains product, in this case 50 Hz because I'm in Europe. We have a very interesting result here which is measuring the ratio of the odd to the even harmonic distortion energies. So we can see from the trace here that it looks like the odd products, the third, the fifth, the seventh, are somewhat higher in amplitude than the evens, here we've got the sixth, the fourth, the second. And this is exactly what this measurement is telling us here, but it's giving us a numerical reading that we can potentially apply limits to, and that gives us a much more useful and faster feedback as to how this device is actually performing. So these spectral processing tools, these smart FFTs, are a really powerful way of measuring all of these types of parameters all at the same time and allowing us to track trade-offs between different parameters as we refine our design, or simply allowing us to quantify all of these results in a very short space of time if we're interested in verification testing or potentially production line testing applications. So that concludes my my brief overview of a couple of areas of power amplifier testing that I wanted to talk about. And so finally I'm going to move on to the electroacoustic components in the system, the drive units and their associated enclosure. Once again, the test system is very similar, or the test setup rather is very similar. I'm again using the D-scope system. This time I have a slightly different setup in that I'm using a microphone and a power supply in order to detect and route analog signals to the D-scope analog input that originated in the acoustical domain. So I'm actually measuring the acoustical output from the drive units of this loudspeaker that we're analysing. And as we said at the beginning of the presentation, we feel that it's very important to be able to measure the electrical and the acoustical performance of the loudspeaker that we might be interested in testing using a single instrument. It makes for better workflow, it allows us to invest in just a single piece of test instrumentation, and it's something that our customers have been asking for some time. So we've been developing electroacoustic testing tools that are now part of the D-scope test package. So let's switch to this last demonstration here, and I will need to just quickly make another adjustment to my test setup so I can actually make a measurement here, which I've now done. So first of all, I'm just going to recap the impulse response based technique that we briefly looked at earlier, and it sounds like most of you are familiar with this already. But the basic idea is that we produce an impulse response. Now, we don't actually apply a true impulse to the system. A perfect impulse has infinitely narrow duration and infinitely high amplitude, and that is infinitely impractical in the real world. So what we do is we use a broadband stimulus, which can be a range of potential signals, ranging from maximum length sequences through white noise, pink noise stimulus. In this case, we're using a swept sinusoidal signal, a chirp, and I'll explain a little bit more about that in a second. But what we do is we set up a broadband stimulus in the signal generator, and we compare the FFT of that data to that of the data that arrives at the analyzer. Once we have made that comparison, we can mathematically derive this impulse response, and as you'll almost certainly know from the feedback you've given me so far, the advantage of using an impulse response technique for an electroacoustic measurement is that if we don't have a perfectly anechoic measurement environment, we can isolate the fundamental impulse from any discrete reflections. And if I just zoom in a little bit here on the impulse response trace, you can see that at this point here we have quite a strong early reflection. I've got quite a small room that I'm actually talking to you from at the moment, and we have an early reflection there which we really don't want to include in our measurement because it will cause comb filtering artifacts that will give us a false impression of how the system's performing. So we can apply our time domain window to gate out or remove any of these early reflections and indeed the late reflections, and to give us a quasi-anechoic frequency response measurement without needing to use an anechoic chamber. Now, I mentioned that we're using a sinusoidal sweep, a chirp signal, and I'm just going to open the generator just to show you that. Oops. So this is our chirp stimulus, our fast swept sine, and In this particular case, I have set up a logarithmic sweep rate. Now, some of you may know this already, but the reason for, or the primary reason for using this particular stimulus is that when we used a logarithmically swept frequency in the swept sine stimulus here, that allows us to do more than just simply analyse the fundamental frequency response of our loudspeaker. And to illustrate that, I am going to just turn off these two traces here and zoom right out to the end of my impulse response. Here you can just about see at the left-hand edge of my screen I have the fundamental impulse. I have a number of cursors marked towards the end of the impulse here, and if I zoom in on these, you can see here that there are a number of additional discrete impulses, and these correspond to the harmonic distortion energies of the transducer that we're measuring. So this is the second harmonic, this is the third harmonic, the fourth, the fifth, and so on upwards in frequency. So with appropriate processing tools here, we can actually extract distortion information from the same impulse response that gives us our fundamental frequency response. And to illustrate that, I'm just going to turn on distortion analysis here up to the fourth harmonic in my measurement setup, and I'm then going to repeat the test. So let's hit the button again. And once again, there's our red fundamental or frequency response trace that we saw in the previous measurement. But we have an additional series of curves now. We have a second harmonic, a third harmonic, and a fourth harmonic distortion trace. So that just very briefly gives you a quick overview of some of the things that you can do with impulse response based analysis of electroacoustic devices. Of course, as with all the topics that we've discussed today, there are many more things that we could potentially talk about, but unfortunately time is against us, so I've packed as much in as I thought I could in the time that we had available, and what I really want to do now is I just want to summarise very quickly what we have talked about today. We've talked about a number of different areas of functionality, which include everything from, in the case of my loudspeaker on the bench here, the USB audio input to the system, through potentially digital audio interfaces at board level, effects process, or rather signal processing, including dynamics and filter sections, through to power amplification and the acoustics of the drive unit in the enclosure. Now, what I haven't gone into any detail about is the fact that we can actually automate all of this, so all of the tests that you've seen in this presentation here are as valid at a production line or QC level, or even a verification testing engineering level, as they are in the sort of manual mode that I have been taking you through today. So for now, I'd like to thank you all very much for your attention. I hope today's session was interesting and useful for you. If you do have any feedback on the session, any suggestions or requests for future content or for further information on today's content, then please do get in contact with us. I'm here on the applications team to help answer any of those kind of questions and to put together future educational events that will hopefully address your specific needs if we haven't already done so. So please feel free to communicate with us. But as I say, for now, thanks a lot, and I will sign off for now. I hope to see you at another webinar event in future. Thank you very much, and goodbye from us here in the UK. Goodbye.